Now let's take an example of one application, say a temperature monitoring application. So this application may have three different tasks. I shown this example before also. So the task one may be handling sensor data gathering from temperature sensor, and task two may be updating your display to show the current temperature value, and task 3 may be taking user input. So to implement this application, you have to create three FreeRTOS tasks, isn't it? Whenever you use the term create, that means some memory is allocated for that creation. So when the task 1 is created, there will be one TCB is being created that we call task control block. Okay, that is specific to a task which is being created. So if you create three tasks, that means you have created three task control block in the memory. So you may be wondering, when you create a task, where the task control block will get created. If you create them dynamically, then they are created in heap memory. Otherwise, you can allocate memory for them statically, so then they will be created in other RAM regions where your global variables and arrays are being stored. So usually we create a task or any other kernel objects of FreeRTOS dynamically. Okay, and each task will be having its own dedicated stack. Okay, so remember one thing, in a multitaskable OS environment, each task will carry its own stack space. So in this case, you are creating three tasks, isn't it? So three control blocks will be created and three individual stacks will be created. The stack size will be mentioned during compile time of the FreeRTOS kernel that we'll see later. So consider a RAM in your microcontroller from the initial address to the final address. So in this RAM, a part of the memory will be reserved for heap. So who decides the starting address and size of the heap? So this is an important question. So who decides that from where heap memory should start? Should it start from here or from somewhere here or whatever? So who decides it? And who should decide where it should end? Okay, that means who decides this length or size of the heap? By default, FreeRTOS heap is declared by FreeRTOS kernel itself. That is place from where it should start, and the size of the heap will be decided by your kernel itself during the compile time. Okay, and if you don't want kernel to decide it, then you can set a configuration item. This is the configuration item, config application underscore allocated underscore heap. You can set this configuration item to 1, which allows the heap to instead be declared by the application. So by default, this configuration item will set to 0. Okay, but if you make this configuration item is equal to 1, then you will have the control to decide the starting address of the heap in the RAM. Okay, so let's move forward. Now let's say you have a RAM and this is the space of the heap. So if you make this to say 512, then 512 bytes of memory will be reserved for heap. So now let's see how task creation takes place in this scenario. So when you create a task, okay, by using an API called xtask create. So this is the API to create a task. I will explain this API later. So it's just an API which creates task. Whenever you create a task dynamically, a TCB will be created in the heap region. Okay, that means a memory will be allocated to hold the TCB, and the stack memory of the task will be reserved in the heap memory. Okay, so whenever you create a task, so this much memory will be consumed. That is memory for TCB plus memory for holding the stack contents of the task 1. So whenever you create another task, so task 2's TCB as well as task 2 stack will be allocated next to the first task. So when you create a semaphore, say for example, so semaphore will have its own semaphore control block, and that control block also will be allocated in the heap memory. And let's say you create after that a queue. Queue will have its own queue control block and an item list to hold the queue items. This actually depends on the size of the queue. The heap grows okay, in this direction. So a typical RTOS application will have a couple of tasks, a semaphore, a queue, a mutex, etc. So all these are called dynamically allocated kernel objects. And other spaces of the RAM will be used for global data, arrays, and static variables. Alright, so let's move forward now. Now you came to know that as you create the kernel objects like task, semaphore, queues dynamically, it will actually consume heap, right? So that means there should be some code which allocates memory as you call these functions, isn't it? So it looks like, okay, xtask create may call a malloc inside it to get the memory from the heap, isn't it? Okay, so that means there must be some code which manages this heap memory, right? So in the next slide, we'll explore how this heap memory management is done. So in your PC programming, you know that, okay, it is managed by malloc and free, isn't it? And now let's see how it is done in the FreeRTOS. In FreeRTOS, okay, there are 5 different heap management implementations, okay, that we call FreeRTOS heap management schemes. There are 5 different C files, okay. All these files will implement different ways of managing the heap, or you can say these are 5 different algorithms, and each implementation will have its own advantages and disadvantages, okay. And for example, if you consider heap 1.c, it will give this API pv port malloc, okay. It won't give you any API to free the memory. So if you use this scheme, then you can only allocate memory, you cannot deallocate memory. And like that, there are up to 5 different implementations, okay. You should choose whichever suits to your application, okay. Or you can even implement your own heap implementation, or that is heap management implementation, to do a malloc and free the memory. Okay, so we will discuss all these different implementations later in this course, okay, because this is just an overview lecture. So each implementation will have at least 2 API. One is to allocate the memory and another API to free the memory. So this is a quick overview regarding the FreeRTOS memory management. Okay, so in the next lecture, let's explore about FreeRTOS synchronization and mutual exclusion services. So this is also an overview lecture, so where we will quickly go through the synchronization and mutual exclusion services.